Okay, so maybe we can get started. So today we will continue our discussion from last time, and where we introduced this new topic of fault tolerance. And I'm going to talk about 2 or 3 different sets of techniques that we need to look at from a fault tolerance perspective. The first one is agreement in the presence of faults. We'll talk about what agreement is and talk about a problem called the Byzantine's general problem. Okay? Then I'll talk about dealing with faults from a network perspective, which is reliable communication. To some degree, when we are done gRPC and RPCs and RMIs, we had briefly touched upon this, but we are going to look at it again. And then the third part is going to be on this problem of distributed commit, which is also something you will see gives us both atomicity property, and we'll see how failures have to be handled in that case. So that's what we'll do today. But just to show you what we will talk about next time, because this topic of fault tolerance will at least be 2 different lectures. Next time we'll talk about consensus, and we'll talk about this technique called Paxos, which is quite popular in industry, Paxos and Raft. And then we'll talk some about checkpointing, message recovery, and so on. Okay, so that's the agenda for today's class and the next class. So let me talk a little bit about agreement first, and then I will talk about the Byzantine general problem. We'll skip some of the slides we had already covered last time. So this is where we had stopped. If you remember, I described this simple hardware circuit, a 1-bit circuit, and I said if you don't have any redundancy in A, B, or C stages, you will actually have no output or bad output. And then we said you can replicate each of the element 3 times, have a voting stage that looks at the output and feeds the output to the next stage, and the voters themselves are replicated to prevent the failure of the voting stage. Okay, so every component of the circuit is replicated to ensure that you can deal with failures. Okay, so we'll use that concept to now understand how do you do this. This is just an electronic circuit, right? So we need to now think about how do we build distributed systems or software systems to incorporate failures of various kinds. Right? So the question we will ask is, how should a set of processes in a distributed system agree on the result of a computation? The computation could be anything. It could just be a request you make to a database. It could be an RPC call. It could be a web HTTP request. What that is not as relevant from our perspective. We'll assume that there's a computation or a request that's sent. There's some response coming, and we need to understand how do you deal with failures. We will talk about 2 different types of failures. The first one is what we will call crash failures, and the other is Byzantine failure. Okay, so crash failures essentially means that when the application is up and running, it produces correct results. Okay, there is no problem with the result it produces, but we also assume that due to bugs, okay, the process may hang or simply crash. Okay, in which case it produces no output. Okay, so there are 2 states a process could be in. The process is up and it's functioning correctly, okay, or the process has crashed and it doesn't function at all. Okay, so this is called a crash failure, where processes basically crash and don't stop functioning. Okay, so then the question is, if you have a system where you want to tolerate k faults of a single component, okay, we have different components or different processes in our distributed system. But let's say for any given component, if you want to tolerate up to k concurrent failures, how many replicas do you need to handle crash failures? How many times should you replicate this process? Is the problem clear what I'm saying? Okay, so essentially you want the system to survive k faults and yet continue to function. Okay, so in this case, we are assuming crash failures, which means that processes fail silently. And by that, that's just a term to indicate you are either up or you're crashed. Okay? And we will say that you need k+1 redundancy to tolerate k faults. Okay? So if k is 1, just as an example, if there is a single failure, you need 2 replicas. K+1 is 2 in this case. Right? So if one fails, the other is still functioning. Okay? If you want to tolerate 2 faults, you need 3 replicas, because 2 can fail and then the third one will continue to run and produce results, right? So that's very simple in terms of understanding. So if you want to have crash fault tolerance and you want to tolerate k concurrent faults, you need k plus 1 replica. The degree of replication is k plus 1 to tolerate k faults. Okay. Now let's talk about a different type of failures, which are Byzantine faults. Okay. In Byzantine faults, processes can run but produce incorrect results. Okay. So in crash fault tolerance, we said you only one of two states: either the process is up and functioning correctly, or it's down and doesn't function. Okay. Now in Byzantine faults, you can still have crashes, of course, but we have other types of problems where the process is up but producing incorrect result. Maybe there is a bug that's causing it to produce bad results. Okay. Or maybe there is a problem where the system has been compromised and the malicious adversary is causing the system to produce incorrect result. Okay. So processes can run even if they are faulty. Okay. So now you have a problem where you send a request to a set of components, they all produce results, but you don't know whether to trust the result or not, because each component can be Byzantine faulty. It can produce bad results, can produce malicious results. So how do you trust what result is the correct one, right? So this is called Byzantine faults, and if you want to have Byzantine fault tolerance, you need a higher degree of replication than crash fault tolerance. Okay. So crash fault tolerance says k faults means k plus 1 replica. Okay. We will see that in Byzantine faults, okay, I didn't put the degree of replication here, I put a question marks. Okay, but we'll see that the answer there is, if you want to tolerate k faults, you need 3k plus 1 replicas. Okay, which means if k is 1, simply to have one process that's faulty, you need 4 replicas. Okay, the degree of replication is 4x. Okay, which, if you think about it, is a high cost to pay. So you need 4 machines to tolerate a Byzantine fault of a single machine. Okay, so that's a high price we are going to pay, but we'll also see why we need that in today's class. So let's start with a little bit of a deeper dive into Byzantine faults. We'll look at 2 or 3 different scenarios. Okay, so we'll start with a scenario where you have 2 processes in your distributed system, and these 2 processes are communicating over a network. Okay, just 2 processes. Maybe it's a client and a server. They are communicating over a network, or they are 2 components of a server system. Maybe they are your microservices that are communicating with each other. Okay. In this case, we are going to assume that the processes are simply exchanging 1-bit messages, just to simplify things. So either a process can send 0 or it can send 1 as a message. These are the only messages you can send. Okay. Very simple example. 2 processes that can send messages, the message could either be a 0 or a 1. Okay. But we will assume that the processes are actually operating correctly. Okay. But the network is Byzantine faulty. The network actually has faults. Okay. That means if you send a 0, okay, the network may decide to deliver 0, which means there is no fault. It may deliver the correct message. It may drop the message altogether. It may deliver nothing. You send 0, nothing appears at the other end. Okay. Or the worst scenario is you send 0, the network delivers 1. It flips the message. Okay. So the other end may get no message at all when the message is sent. It may get the correct message, or it may get an incorrect message. Okay. And we don't know what the network will do. It's up to the network because it is faulty. When you send some message, we don't know what is going to happen. Okay. And yet we want these 2 processes to, or we want to ask the question, can these 2 processes communicate and coordinate or reach some agreement in this kind of scenario where you have a faulty network? So in this case, the processes is not the problem, but it's the network that's the problem. Is the question clear? Okay. Now we will try to make this a little more interesting by turning this into a problem that is called a Byzantine's general problem, and this is the first version of it. We'll see another version. Okay. So this is the 2 general version of the problem. Okay. So here we are assuming that there are armies there is an army with, let's say, 2 battalions. We'll just call them 2 armies, but it's the same army with 2 battalions that are waiting to attack. Okay? And the 2 generals of this army want to coordinate the time of the attack. Okay? So they want to decide what time they should both attack their common enemy. Okay? And the way they are going to figure out what time to attack is they are going to use a messenger to send messages back and forth to decide on the time. Okay? The messenger will has to travel through hostile territory. Okay? The territory is a network in this case. Okay? So you can assume that anything can happen to the messenger. You send a message with the messenger may reach the other army and deliver the message successfully. Okay? The messenger may get captured and may never deliver the message. Okay? Or the messenger might get captured and a fake messenger is sent with the wrong message to the other end. Okay? So any of these 3 things can happen, which is the exact 3 things I talked about in the network case. Okay? So then the question is, can these 2 generals send messages back and forth and reach some agreement on what time to attack? Is the question clear? Okay, so how are we going to solve this problem? Any thoughts? Okay, so you can send a large number of messengers and try to get some majority. But we got to come up, yes, we will do something like that, but not exactly, as you will see. But we need to know how the message has been actually delivered successfully. Because the key question you should ask is, how do we know, how do both of those generals know that they have agreed on the time? Okay, so let's just take this as a simple example. Let's say that we'll call these 2 generals A and B, or these 2 armies A and B. A sends a message to B through this messenger saying, let's launch an attack at 9 a.m. Okay, so let us, just for example, assume that the messenger actually reaches the other end successfully and delivers the message. Okay, so now B knows that you have to attack at 9 a.m. Okay, are we done at this point? Is there agreement that A said let's attack at 9, he sent a message to B, B received the message that you have to attack it. Yeah. Yeah, so we have to send an acknowledgement. Why do we need an acknowledgement? Okay, so A needs to know that the message was received, because you said it's a hostile terrain, right? Just because you sent the message, there's no guarantee the message will be received. Just because in this example I said the message is received, A doesn't know that B has received the message. Correct? So then what do? We send an acknowledgement. So acknowledgement is messenger comes back saying I delivered the message. Okay, yes, so now let's assume, again, message is lost, we have a bigger problem, but let's assume the messenger actually reaches the other end, comes back to A and says, I went to B, I delivered the message, and I've come back with this acknowledgement saying I delivered the message. So now A knows that B has received the message and that the message was delivered successfully. Okay, is this it? Are we done now? So we can now launch an attack. Yes, question, is there a potential for the message to be modified? Yes, I said that the message may never reach. The message could be modified. Anything can happen. Okay? In this case, A has actually received the acknowledgement back. The messenger came back. So it could be a different message, but in this example, I just said you received the right message. Okay? If you receive a different message, we have bigger problems. But I'm just saying, let's assume that you received the acknowledgement. The question is this, have we reached agreement? Does A know that it's now safe to launch an attack because you sent the message and got an acknowledgement? No. Okay. Why?
In a fully adversarial case, no matter how many times you send it, get an acknowledgement, it was changed by an adversary every time.
Okay, so in an adversarial setting, you can actually not know what has happened. You can send the message back and forth multiple times and still not know. That's what you're saying, right? Yes. So let me try to break that down. So let's just take this case. A sent a message to B, delivered it successfully. Messenger came back and said, I delivered the message. Okay? So A now knows that B knows to launch the attack at 9 a.m. Okay? But how does B know that A has gotten the acknowledgement? Okay? B does not know that because the messenger could have been captured in transit, and then B doesn't at this point know that A has received the message. So it cannot figure out that it is safe to launch the attack, because all B knows is you got a message, you sent an acknowledgement, don't know that A has gotten it. Okay? So what will we do? We will recurse. We'll say, okay, you can go back and deliver an acknowledgement to the acknowledgement. Okay? So let's again assume that the messenger has reached B. Okay? So now B knows that A got the acknowledgement to the original message. Okay? Are we done? We are not done, because A will not know whether the message was received. So you have the same problem, right? Every time you send an ACK to all the previous messages, you don't know that the message was received at the other end. Okay? So you can do this infinite times, and yet there will be no agreement. You're sending ACKs and ACK back and forth, and yet you're not agreeing that, yes, we should launch an attack at 9 a.m. Okay? So this is an impossibility result. Okay? The result says that two perfect processes, which means that in this case, the generals are actually reliable. They are not traitors. Okay? Can never reach agreement in the presence of an unreliable channel. The network is faulty, which was the same as saying our terrain through to where the messenger goes is hostile, and the messenger can get captured, or the bad message can be delivered. You cannot reach agreement. Okay? So this problem cannot be solved. Okay? And the other thing I want to mention is this term called common knowledge. Common knowledge is basically a term in distributed system which says that what this information is known to everyone, and everyone knows that everyone else knows it. Okay? So here we are trying to achieve common knowledge, which is that A and B both know that the other party knows that you have to launch an attack at 9 a.m. and that the other party also knows that I know. Right? So in most cases, either I know and I know that they know, but they don't know that I know. So you are basically recursing and not reaching common knowledge. So this is a very famous impossibility results, and you cannot solve this problem. There is no way, if the network is unreliable, can you actually solve the problem. Okay? Yes, question.
So then why rely on network?
Okay, question is, why can we rely on TCP to do a three-way handshake? So TCP is not trying to solve the Byzantine faulty problem. Okay? TCP is just setting a channel between two endpoints, but you're not trying to reach agreement. So this is a more complex problem, right? This is not, you're not trying to achieve message delivery. Okay? Message delivery just requires an acknowledgement. Okay? You are trying to actually reach agreement, which is that I know something and I know that the other party knows something and they also know that I know something. That's a different property you're trying to achieve than just establish a connection. If you're just establishing a connection for message delivery, a three-way handshake is fine. I set up a connection, you send an acknowledgement saying you set up a connection. The other way, we are done at this point. We are not trying to reach agreement, right? This is a different problem. Okay? So this is why a three-way handshake or n-way handshake where n goes to infinity still does not solve the problem. This clear? Okay. So so this we cannot solve. So we'll say this is hopeless. Let's not worry about it. Let's now solve a different problem. Okay? We'll now assume that the network is not the problem anymore. Let's assume we have TCP. Okay? TCP gives us a reliable channel. Okay? So we don't worry about it. TCP will take care of network retransmissions and corruption of packets in the network, etc. So we know now we have a reliable channel for our application. But let's say now the generals are the problem. One of the generals is a traitor. Okay? So we have n generals. Okay? In the broader cases where m out of n generals are traitors. Okay? In this example, we have 4 generals, 1 through 4. The gray one, which is number 3, is a faulty process, or that's a traitor. Okay? So what does that traitor mean? So in this case, the messages are going to go reliably. Okay? but when the messages are exchanged, the traitor can send bad messages. It can send incorrect messages. Sometimes it can send the right message. Sometimes it may decide not to send any message. Sometimes it can send incorrect messages. Okay. So question is, in this case, can we reach agreement? Okay, agreement means you have to, other generals have to identify who is the faulty process or who is the traitor, and then the rest of them still have to agree on something. Okay, so you want to identify the faulty process, eliminate it from the decision making, and reach a decision. Okay, is that clear? So three loyal generals, one traitor. Okay, we'll change the problem slightly here in that we are not going to decide on what time to attack, but let's say the generals are exchanging how many soldiers each of them have to launch an attack. Okay, doesn't really matter what the message is, but this just makes it easier to understand. So you are sending your troop strength in the number of kilo soldiers in this case. That's how many thousands of soldiers do you have. Okay, so for simplicity, we'll just assume that general 1 has 1,000 soldiers, 2 has 2,000, 3 has 3,000, and 4 has 4,000. So they're supposed to send 1, 2, 3, and 4 as their messages to the others. Okay, so we'll now essentially develop a technique where each soldier is going, each general is going to send their troop strength to the others. Okay, and we want to reach agreement where you know everyone else's troop strength and you know yours, so you know how many soldiers you have in the army in the aggregate. That's the problem we are trying to solve. Okay, that's the agreement we want to get to. Okay, so one is going to send message 1 to the other 3. Okay, and that's going to go through fine. It's going to reach the others. 2 is going to send 2. Okay, 4 is going to send 4, but 3 can do whatever it wants. It's a Byzantine faulty process. So if it wants, it can send 3. Okay, or it can send 3 different numbers to 3 different generals, which is why we say it sends X, Y, and Z. Okay, these we just call them variables because they can take any arbitrary value. It's a Byzantine faulty process. Okay, it can send 3, it can send 3, 4, 5, it can send whatever it wants. Okay, so we don't know what it's sending, so it just sends some arbitrary message. Okay, they may match, they may not match. We don't care. Okay, we just need to still figure out how to reach agreement. Okay, so at the end of round 1, okay, general 1 gets 1, 2, X, and 4 as the vector. Okay, so it knows it has 1, 2 sent it 2, 3 sent it X, 4 sent it 4. Okay, 2 is going to get 1, 2, Y, and 4. Okay, 3 is going to get 1, 2, 3, and 4. It gets the right messages. It knows how many soldiers it has. So 3 is faulty, but it actually got the right values. Okay, and 4 is going to get 1, 2, Z, and 4. Okay, so this is what happens at the end of round 1. So at this point, we have not reached agreement. We just got the first set of messages where each general said this is the amount of soldiers they have. Okay, now what we will do is in round 2, we will take those messages and send them back. This is like sending acknowledgement, right? So we want to say, I got these messages. So instead of sending an acknowledgement, you will send each general will send the vector it receives back to everyone else. Okay, so 1 is going to send 1 to X and 4 to all the other 3 and so on and so forth. Okay, but 3 can again do whatever it wants. Okay, it will send some arbitrary message. In this case, instead of X, Y, Z, let's say it's going to send A, B, C, D or something like this. Okay, which are variables, so that can be arbitrary. Okay, so in the round 2, this is what you will see. Okay, you will get vectors from others. So you will get 1 will get 1, 2, Y, and 4 from 2. Okay, is going to get A, B, C, D from 3, and is going to get 1, 2, Z, and 4 from 4. Okay, and 2 is same way. Okay, but it will get 1, 2, X, 4. It will get some other garbage values from 3, 1, 2, Z, 4 from, okay, and then 4 is going to get similar values. Okay, is this clear? So at this point, you can identify that the value, because you have now this vector, you can see that whatever 3 is sending is not matching. Okay, because you are getting others are telling you 3 sent at some value, they don't match, but 1 and 2 and 4 are actually matching. So you know now who is the traitor because you identified who is sending bad values. Okay, because that column and that row will not match. Okay, but the others are sending consistent values. Okay, so now you identified that 3 is a traitor, it's sending bad values, so you can eliminate it from the decision making, and then 1, 2, and 4 can take their values, which is 1, 2, and 4 in this case, and say that's the troop strength, and you cannot actually rely on 3 in this case. that clear? Okay. So in this case, in 2 rounds, okay, which is like sending a message and getting an acknowledgement, you could identify the process that was sending bad messages. Okay, because what happened is you had everyone send a message and you had everyone else tell everyone else what message they received from others. And because 3 sent different values to everyone else, you could identify that. Because others told you this is what 3 sent me, and you can figure out that it's sending different values to different processes. And then you can essentially get rid of 3 and reach agreement. Okay, yes. What if it sends same wrong value? In this case, that doesn't matter, okay, because you will see that they match. Okay? So because the point here is not to see that the values actually mean something. So let's say this was a computation, right? You said what's 2 plus 2 or something like that, right? So 3 is sending some garbage value, so you know it doesn't match. Right? So yes, it could send the same wrong value, but if they match in this case, we don't care, because we assume that it's actually sending consistent. We are more worried about, in this case, sending the same consistent message than the actual value of the computation. But if this was an actual computation where you're sending requests, that would matter. Right? Then you will know that it's sending wrong results, because the other say 2 plus 2 is 4 and 3 is saying some garbage. Okay, is that clear what we just said here? Okay, this is called the Byzantine general problem, and essentially what we have done is identified a faulty process, eliminated from the decision making. The other 3 are voting effectively by saying what did each of us see and what should we agree on. Okay, and then you can get to a situation where you can come to agreement, okay, which can figure out what to do. Yes, question. Okay, 3 will also get 3 sets of values, but we don't, since 3 is faulty, it's not actually going to have 1, 2, and 4 listen to what it's trying to say, right? So question is, if 3 gets 3 sets of values, how do we decide which is faulty? So let's take 1's perspective. This is the vectors that 1 got. Okay? Just looking at these vectors, what does it tell you? Okay? So you will see that 1, 2, and 4 are matching across these 2. Okay? But this row and this column don't match, which means that whatever 3 sent it and whatever 3 sent to others is not matching. Okay? So you eliminate that, and so one can figure out that 2 and 4 are reliable processes. It assumes it's reliable, but it knows that 3 is not reliable. Okay? 2 can repeat the same process, it will reach the same conclusion, and 4 can repeat that process, it will reach that conclusion. So each generalist can now depend on 2 others and eliminate 3. Okay? Yes.
C actually sent different values the first time, but the next time maybe it just sends white. So in that case, how will we know which one is actually the?
Okay, so the question is, if 2 send different values the first time and it sent the same value the second time, what happened, right? So it shouldn't matter, because X, Y, Z, A, B, C, D, and X and Z are variables. They could be same, they could be different. If there's any difference between any of them, okay, there will be a mismatch. You will see that whatever 3 is sending is not matching.
No, but if 3 is sending 1, 2, Y, 4, now it looks like 3 and first one's and the third one.
Can you repeat what 3 is sending? Are you talking about the second round or the first round? Second round. Okay.
One is sending 1, 2, Y.
Yes. Yes.
Case 1, 2, Y, 4 is shared between what 1 got for 2 cases, but the third one is 1, 2, Z. How will it know?
Right. So if Y, Y, Z will not match, because it will tell you that 3 send Y in the first round to 2 and send Z in the second to the third one. Right. You have to send the same value to everyone. If you send to any different values, you can figure out that 3 was actually not sending the same values.
But wouldn't that look like 4th one sent the wrong?
Question, you are saying, would it look like the 4th one sent the wrong value? You are actually looking at 4th column to see what its values. Okay, this is just 4 telling you what 3 sent it. Okay, as far as 4 is concerned, you only look at the 4th column, not the 3rd column. Okay. Yes.
Something which is not correct, but it consistently sends same result,
Yes.
then this would.
The question is, if 3 sends an incorrect result, but it's the same result, this would not work. Okay, that was a question that was actually asked earlier. In this case, we are just asking it to send the number of soldiers it has, right? So long as it's consistent, we are just believing it. Okay, but what you're saying is correct in that if 3 sends the wrong information, you will get them to believe the wrong thing. But the answer to what I said is, suppose these were not send me how many soldiers you have, but I send you a request and say, send me the result of 2 plus 2. Okay, so you perform a computation and you send a result. Okay, in this case, if you actually send 2 plus 2 is 5 and it's consistently sent 5, but the others are saying 2 plus 2 is 4, then you know that that's which one is wrong. Okay, and so when you do computation, you send the same request to 4 replicas and say, give me the answer, and then you run this protocol and figure out which ones are right and which ones are wrong. Okay, any other questions here? Okay, so we will now, so this we did with 4, okay, and we could figure out which one is the traitor. Okay, let's repeat this with 3. Okay, so in this case, you have 3 is still the traitor, but there are only 3 generals in this case, 1, 2, and 3. Okay, 1 and 2 are sending correct values, and 3 is sending garbage value because it's Byzantine faulty. Okay, so again, we'll do the 2-round protocol, right? So at the end of first round, 1 gets 1 to x, 2 gets 1 to y, 3 gets 1 to 3 because it knows its own value. And then you say each broadcast this out. Okay, so at the second round, 1 gets 1 to y from 2, and it gets a, b, c from 3. Okay, 2 gets 1 to x from 1, and it gets d, e, f from 2. Okay, so now you know that you, as in 1 and 2, know that there is a mismatch. Okay, because these values are not matching. Okay, but you don't know which process is faulty. Which process sent you garbage value is not clear, because is this a, b, c the correct value, or 1 to y is the correct value? You don't know. Okay, because they just don't match. In the previous case, you actually could look at others saying that there's 1, 2, 4 was matching for these 2 vectors. So you could say these are correct and this is wrong. In this case, one of this is correct and one of this is wrong, but you don't know which one. Okay, so you cannot, you know that there is a fault, but you don't know which process to trust. Right? So it's like you have 2 friends, you ask them something, one of them lied to you, so the answers are different, but you don't know who lied. Right? Because they are just giving you different answers. So same thing is happening here. One is hearing 2 different answers from 2 and 3, but it doesn't know what to believe in this case. Okay? So you cannot, in this case, reach agreement. Okay? You can figure out there is a fault because the answers don't match. Because if you say what's 2 plus 2, okay, you're essentially going to get 2 different answers from these 2. But you don't know which one to. I mean, of course, if it's 2 plus 2, you can figure out. But let's say you're doing a database query and you got 2 different results, you don't actually know which one to trust. Okay, so this is why you need 4 processes, not 3. If you have 3, then that's not enough. Degree of replication of 3 can get you a state where you know there's a fault, but it cannot help you figure out what the fault is. Yes, question.
So here, that because we're in a decentralized system, we need 3m plus 1. If we had a trusted coordinator, then we could reduce this to 2k plus 1.
Okay.
Just as a flow.
Yes. The question is, if you had a trusted coordinator, you only need the other 3, and the trusted coordinator can vote. But we have to still count that trusted coordinator as one entity in the process. So you still have, yes, you're absolutely right. If you added another process here and there was a coordinator, you are just voting, and 2 out of 3 match, that's still good, right? But you still have 4 elements in the system, which is why no matter how you see it, you still need 4 elements. But you're right. If you have a coordinator, you need 3 other replicas, but there is a coordinator which still counts as one part of the system. Okay. Is this clear? Okay, so this is all Byzantine fault tolerance. So this should tell you the theorem that you should have in mind is, first thing is we can solve this problem, as opposed to when the network is Byzantine faulty, we cannot solve the problem at all. Right? So when the processes are faulty, so the good news is you can solve the problem. And if you have m faulty processes, you need essentially 3m plus 1 total processes in the system. to deal with it. Okay? So when M is 1, that was 4 processes. Okay, that means if there's one traitor, you need 4 processes. There are 2 faulty processes. Okay, that's essentially 7 processes. So 7 degree of replication to deal with 2 faults. Okay, so you will see Byzantine fault tolerance is very expensive. Okay, if you say design a system to make deal with Byzantine faults, to just have one component fail and be Byzantine faulty, you have to buy 4 machines. Okay, you have to have 4 degree of replication. So cost of your system has increased by factor of 4. Okay, as opposed to crash faults. Okay, I said k plus 1, right? That's very straightforward. If k or m plus 1, which is if m is 1, you need 2 machines, which is easy. One fails, the other one continues to run, right? So that's much cheaper for crash fault tolerance. This is very expensive. Okay, so many systems will not actually implement Byzantine fault tolerance. Okay, but this is the number of replicas you need. Where this has become popular is things like Bitcoin and cryptocurrencies, where you need that high degree of assurance that you have financial transaction, so you will pay that price. Okay? But for a web application, typically not. And you're not going to have 4 machines just to deal with one fault. Or you'll assume that only crash faults need to be handled. There are Byzantine faults, then you will not handle them at all. Just clear, yes. Okay, question is, how do we know the number of faulty processes in the system? So this is going to be not known. This is what you design the system for. Right? So the developer has to say, I want to design the system to deal with k equal to 1 fault or 2 fault, and then you decide how many. Okay? So if you're more than that, which is possible, system will not work. The system is only guaranteed to work so long as the number of faults is no more than m. So that's what you designed it. Right? So you have to think about that and design it with the right m. Yes. So question is, when you're querying a database or sending requests, how do you know the number of faults is more than m? So you will not know that. That's what I'm saying. If you have a system designed for m faults, it will only work correctly if there are at least m faults. Right? If you have more than m faults, it will still produce some results, but at that point the results are not trustworthy, and you will not know, because that's what you designed it for. Crash fault tolerance is easy. Right? Crash fault tolerance means that you don't produce bad results. You either produce correct results if you're up, or you crash and produce no results at all. Right? So in crash fault tolerance, if you have more than k faults, your system stops working, because you basically have k. If you have k plus 1 replicas, more than k faults, then all machines crashed, and system doesn't work. Right? So that's the same kind of stuff will happen here. Of course, you can have more than m faults, but if you did not design for it a priori, at that point you will not have fault tolerant guarantees in the system. What is the benefit of choosing threshold? First thing is, most systems will barely stick to m equals 1, because anything more than that gets very expensive. But yeah, the general property says you can pick whatever number of faults you want. And the benefit is higher degree of m means that you have greater degree of fault tolerance in the system. Right? So you can tolerate bigger problems that can occur. Maybe there is a earthquake and lots of things get destroyed. Maybe multiple data centers go down, but there are some distant data centers that are still up. So you may have more than one m machines failing at the same time. So it all depends on what kind of failures. Right? It could be network outage, power outage, natural disaster. Any of these can, or an actual hack into the system can also make things Byzantine faulty. You have to design for this. Okay? Yes.
We can get a simple. We got one. We're good one. Why do you need
Right. So the question is, why do you not need simple majority? So the way you want to think about it was the question that was asked earlier. Right? So let's say you have one voter that's just taking votes, and others are the ones that are actually sending answers. Okay? So if you have one voter, you need at least 3 machines so that the other 2 outvote the third one, right? Now, you can actually, now let's say you want to have 2 faults. You are saying I need m plus 2. Is that what you just said? M plus 2, yes. So if the voter doesn't fail, that's correct. If the voter is not faulty, then you need m plus 2, but any 2 components can fail in this case, right? So you need to make sure you need to deal with these types of problems. Okay, so which is why you get to 3m plus 1, which is a lot of replication. Yes.
Because greater than m based on the results getting.
So question is, can you detect which machines are faulty based on results being inconsistent? Is that your question or no?
For that, you're not handling whatever m is, probably there's more machines than m.
Yeah. So if you have more machines and M failing, you can't detect anything because they can give you bad results, and you will be back to this problem where they will not match. So you know that there is a problem, but you don't know what is the right answer. Okay.
But you'll be able to know that there is a.
Yes. So you will need to know. So if you only want to detect failures, 2m plus 1 is good enough. If you want to handle failures and actually produce answers, 3m plus 1 is necessary, right? So if you have greater than m, so long as that m is not much larger, you will see that there is a problem because your results will not match. But you cannot produce an answer at that point. The system will stop working. Okay? Because the voter will not be able to figure out what is the right answer. Okay. All right. So that's Byzantine general problem. It's a classic problem in distributed systems that deals with Byzantine faults. But here is basically what we discussed. Yeah, these are the properties. Detecting a faulty process. Okay, 2m plus 1 or 2k plus 1 for m faults. Okay, so that's just saying I need to detect that something has gone wrong, not necessarily produce an answer. But if you want to reach agreement, which is I detect, isolate the faulty processes and produce the correct answers, 3k plus 1. Okay, 2/3 majority is needed always to deal with k faults. Okay, high degree of fault tolerance. Okay, so implication on real systems, quite expensive. Okay, so you better have use cases where you will pay that price. As I said, the place where this has become widely deployed is things like cryptocurrencies, where you have a distributed ledger where you are writing entries, but you want all the entries to match and whatnot. So there you don't want faults, or you don't want somebody to be stealing money and things of that sort. So that's where you will pay the price. For many other applications, they deal with only crash faults. They will add much lower degree of replication, typically not Byzantine faults. Okay? So that's the kind of design decisions that are made in real systems. Okay, so we'll switch gears. If there are questions, we can still talk about them. Otherwise, we will switch gears, talk about communication, okay, and then we'll talk about distributed commit, which is the last part. Okay, so this is something we have somewhat encountered when we talked about TCP sockets and things of that sort. You'll remember that when we talked about RPC semantics, I had briefly mentioned there are quite a few problems that can occur when the client cannot locate the server, the request message is lost, the reply message is lost, the server crashes, okay, client crashes after sending the request. And we had some techniques which we talked about in lecture 3 that said, how do you deal with lost messages? You do retransmission. What happens if the server crashes? You keep retrying until it comes back up. The client crashes, then the server can just stop processing the request, not send reply. So we talked about that a while back. Okay, actually in lecture 3, let's assume that we know that material, and we'll now talk about other types of problems, not just messages getting dropped, okay, which is what this basically told us to end. Right. So in particular, we will now talk about one-to-many communication, which we have not looked at so far. We only talked about one-to-one, which is the client sends a message to a server sends a reply, and so on. But there are many cases where you will have one-to-many communication. Okay, one sender, okay, multiple recipients. Okay, and this is going to often come up in distributed systems because we talked about replicas just in the last class, where you make a write, and I have to send that write to all my replicas so that they're all consistent. Okay, that's a one-to-many where the primary is sending multiple same write messages to multiple recipients. Okay, saying that perform this right so that there's consistency. So in distributed system, when there's replication, one-to-many communication is often used for the replicas to talk to one another, where they want to send the same message to other replicas. Okay? So this is going to be done through a technique called multicast. Okay? Multicast essentially means that you do a send and it's received by n other recipients. Okay? Broadcast means when you send a message, every other machine on that network, a local area network, typically receives it. So broadcast means everyone. Multicast is just going to a subset. Unicast is one-to-one. Okay? Whatever we talked about is technically referred to as unicast messages in the networking world. Okay? But now we'll talk about multicast. Okay? So here is our example where the multicast says there is one sender, there are 4 receivers. Every message is sent to all the receivers. Okay? And we are going to essentially see how to do this in a reliable fashion. Okay? Now, we know how TCP/IP works. Okay? In TCP/IP, when you sender sends a message to the recipient sends an ACK. Okay? And when the sender gets the ACK, you know that you have received the message. We are not trying to reach agreement or anything there, right? We are just saying, does the sender know the message was received or not? That's fine. The receiver doesn't need to know that the sender got that. That's not the problem. Problem is, does the sender know so that he doesn't have to retransmit? So we use simple acknowledgement-based schemes in unicast. Okay? Question is, can we use acknowledgements in multicast to get reliable delivery of a multicast message? So let's ask that question. So every time sender sends a message, is going to send the same message to 4 other receivers. Okay? In this case, each receiver has to send an acknowledgement. Okay? So if the sender gets 4 acknowledgements back, it knows all the receiver has received the message. Okay? And it can send the next message and so on and so forth. That's just generalizing how TCP works to a multicast scenario. You just use ACK-based schemes to send these messages, okay, and get acknowledged. Is that clear? How can I send? So this is also called group communication, by the way, because you're sending messages to a group of recipients. Okay? So you send a message to a group. Every member of the group, when they get the message, send an acknowledgement. Okay? And when you get all the acknowledgements, you know the message has been received. Maybe you only get 3 ACKs in that example out of 4. So you know that one of them has not sent you an ACK. You can time out and just retransmit to that one. Okay? So you can do the same thing you do in TCP/IP. As an example. So if you don't get an ACK, you basically time out and returns. Okay? But now you should ask the question. So this is a simple ACK-based scheme. But let's ask the question, what happens if the group size is very large? Here it's 4. Okay? Let's say you're sending a message to 4,000 machines, not 4 machines. Okay? So you send one message, okay? Your multicast socket. Okay, so you just still use socket-like thing. You'll only send once. You're not sending n times. You send once, the network will deliver it to n recipients. Here n is 4,000. Okay, so if you use ACK-based schemes, you will have to wait for 4,000 acknowledgements to come back. Okay, and you have to process all of them. Okay, so now what does this tell you from a sender's perspective? Yes, sender is going to be waiting for lots of acknowledgement and processing them. Okay? Load on the sender is high. Okay? So for every message, it has to receive n acknowledgements, and if n is large, it increases the burden on the sender. Okay? So ACK-based scheme, so this is another way of saying ACK-based scheme don't scale when the group size is large in a multicast system. Okay? Because the larger the group, the more the acknowledgements that have to come back. Okay? And the sender's load is going to just keep going up, because sending message is not the problem, but checking that the message was received is a problem. You have to now receive lots of acknowledgements. Okay? So what can you do in this case? You can use what is called a negative acknowledgement or a NAC. Okay? You are going to turn this around and say that the sender does not want to process 4,000 acknowledgements. So we will say, if you receive the message as a recipient successfully, don't send anything at all. Okay? But if you don't receive a message, okay, send a negative acknowledgement saying I'm missing something. Okay? This is called a NAC, a negative acknowledgement saying I didn't receive that message. Okay? Yes.
How does the recipient know that it is sent?
Yes, that's my question too. How do you know you did not receive a message? If you didn't receive it, when are you going to send a negative acknowledgement? To send a negative acknowledgement, you first need to know you didn't receive something. That clear what the question is? Okay. So the answer is not that hard to understand. We'll assume that the sender is sending more than one message. Otherwise, this doesn't work. You're sending only one message, and I'm a receiver. I never receive it. I don't know. I need to send a NAC. So that will not work. Okay. But if you're sending more than one message, okay, we will assume that messages are numbered. Okay. That's how TCP works too. They have something called sequence number. So every message is numbered. Okay. So as a recipient, I received, in this case, you will see I received message number 23, and then suddenly I get message 25. And we'll say our messages are being delivered in order. So I know I received 23, I received 25, I know I'm missing a message. This is when you're going to send a NAC. So you have to receive the next message for you to send a NAC for the previous message if you didn't receive it. That's the way it's going to work. Right? Because you don't know if you don't get something at all that you didn't receive the message. Okay? So you'll only send NAC when you receive a subsequent message, or maybe there is even a gap. You receive 23 and then you suddenly receive 27. I know I have to send a NAC for a sequence of messages in the middle. That can also happen because packet losses can actually not be random. They can be constrained, and a sequence of packets can get lost. But whatever it is, you are sending sequence numbers or you are numbering messages. We're assuming messages are going in order. So if you receive a message and you see a gap in the from the previous message, you send a negative acknowledgement. That NAC is, in this case, you will see the NAC goes not just to the sender, but maybe it can go to other nearby receiver. So either some other receiver, if it still has the message buffered, or the sender can then resend the message. Okay. So that's how you will have negative acknowledgement schemes. Okay. The only other issue in negative acknowledgement is the last message is going to have that same problem, right? If I'm on this is my last message, I need to know that I actually got it. So I might need to send some additional dummy messages after the real last message so that a NAC can come back for the last message. Otherwise, there is no subsequent message after that. The last message in the sequence get dropped. The receiver will not know to send a NAC. Is this clear? Yes, question.
One that comes after the gap, that is getting message like
Yes, the question is, if you get a later message 27, will you keep that and receive send negative acknowledgements? Yes, so that is what will happen. This is basically at the network level. You will buffer the message that came. You will send negative acknowledgements. You will get all of them. Once they all come, you will give them to the application in that order. Right. So essentially, you will see here, if you look at this, you will see that M25 was received. Okay. So this receiver is going to buffer it, is going to send a negative acknowledgement saying miss 24, and is going to get that message. Okay.
But what will the last value that let's see if it again fails in the second process? Last year,
so you are saying if that message again doesn't reach, right? So the negative acknowledgements can have a timeout mechanism, right? So I send a negative acknowledgement. I wait for the message to come. If it doesn't come in 500 milliseconds, I time out, send another negative. This is how TCP also sends ACKs, right? So if you basically, you can retransmit if I don't receive my ACK and things. So you can have timeout value. So this receiver might have to send multiple NACs to get the message, because NACs can also get lost, right? We are not assuming the network is reliable here, right? So your application is seeing a reliable abstraction, but the real network is lossy. So you have to retransmit multiple times sometimes. Yes. Yeah. So figure B is actually showing you a case where you are sending both ACKs and NACs. That's not what you will do. Okay, this is just to show that the overhead is high. So the third figure shows you a pure NAC-based scheme. Okay. If this was an ACK-based scheme, this would not have sent anything at all, right? For you didn't receive 24. You'll send an ACK for 25, but not 20. Is this clear? Yes. Yeah, so that's a good question. The question is, what if 24 arrives after 25? That's your question, right? So two ways to think about it. One is we can assume in order delivery, in which case the network will not cause that to happen. But that's not true in real networks. In real networks, packets can be delivered out of order. But from the receiver's perspective, it doesn't matter. It send a NAC. If 24 just arrives afterwards, not because of the NAC, just because the network delivered it late, that's okay. It'll get 24. Maybe another 24 will come because you sent a NAC, but you have the sequence numbers and you know which ones have been received. So any duplicates can also be thrown away. Right? So you have to do all of that extra work, but that's okay. That's not a problem. Okay? Yes. Okay. The question is, what if some of the messages from the sender are supposed to be received by a subset of receiver, right? Yeah. So if you have a need where some messages lost, in this case, there are 4 receivers and 1 sender, right? So if you have a need where some messages need to go to only 2 machines, other need to go to 4 machines, what you will do is you will construct multiple multicast groups. So this is like you will have 2 sockets, 2 multicast sockets. In the first socket, maybe only 1 and 2 are subscribed to the socket. In the second socket, all 4 are subscribed to it. So if you want to send a message to only 1 and 2, you will send it on the first socket, and that will only deliver it to 1 and 2. If you want to send it to all 4, you will send it to. You can construct multiple subgroups. Okay? Each of them will have its own socket, and that socket will basically tell you that if you send a message to that socket, which subgroup will receive it. Right? This is somewhat like mailing lists, right? So you can think about there are n students. If you want to have a list with only 2 students, you'll construct one mailing list. If you want to send it all, you'll construct another mailing list, and you will send it once to the list, and the list delivers it, right? That's exactly how multicast will work. So you will not send a message to all the members. If you want to only send to a subset, you'll construct another group and send it to that group. The question is, the sequence numbers, are they updated per group or for all the messages? Sequence numbers are on a per group basis. So if you have one group, they will have their own sequence numbers from the other, because those are distinct messages you're sending, right? You don't mix them up. Is this clear? Okay. All right. So that's reliable communication. We'll talk a little bit more and then get to distributed commit. So there are many. So that's the basic abstraction of multicast, but there are many higher level properties you might want to know. These were the kinds of questions that were just asked. So first one is FIFO property. Okay, it's called broadcast, but you can think of it as multicast. FIFO property says if a process, a sender sends M1, then sends M2, then all processes in the multicast group must receive M1 before M2. There's no reordering by the network. Okay, so if you have that additional property, if you have a multicast protocol that guarantees FIFO, that says each sender, whatever it sends, is delivered in order, no reordering. Okay? By default, you will not get that property. Network can reorder messages, but you can implement additional mechanisms to ensure FIFO delivery. Okay? That's one. Okay? Or you can do totally ordered delivery. Okay? This is like our Lamport's clock saying if 2 processes send M1 and M2 and they're ordered based on Lamport's clock saying M1 happened before M2, okay, then they should also be delivered in that order. So receive are to be delivered as well. Okay? So that's totally ordered. Causally ordered simply says if send of M1 was before send of M2, again thinking about Lamport's clock-like approaches, receive of M1 happens before M2. This one puts a total ordering, that one just puts a partial ordering only on causally ordered messages. But what both of those say is that not only should you order messages from a single process, which is what FIFO does, you should try to order sends and receive across processes, which is what these 2 techniques do. Okay? And then we have some other techniques which basically are called state machine replication. We will get back to this state machine replication in about 2 classes when we talk about consensus. Okay? Because that also involves writing to disks and so on, log replication and whatnot. It requires multicast, but it requires many other techniques. So this part will hold off. But this should tell you that in addition to multicasting, which says I send things to a group, I may need higher level properties. Order the messages. Okay? Order messages across senders. Okay? Order messages based on either a total ordering or causal ordering. Okay? So depending on what you do, you will get different types of multicast libraries or group communication libraries. Okay? Yes. Should FIFO broadcast imply total order? No. Total ordering will actually imply FIFO broadcast, because what can happen is in FIFO broadcast, you have two senders. Okay? Each sender is sending a sequence of messages. Okay? All that is saying is I should receive the messages from each sender in order, but two receivers can receive them in different interleaving. Okay? So I can receive message 1 from sender 1 and then message 2 from sender 2 is as 1 and 2 in one case, and 2 and 1 in the other case. That's still FIFO because you're only ordering per sender. You're not ordering the interleaving. This is ordering the interleaving. This is saying that we have an actual order across senders. Okay? So total ordering will imply FIFO, but not the other way around. Is that clear? Any other questions here? Okay. So a few more things and then we'll get to distributed commit. So here's a different technique called atomic multicast. Okay? So this one is now going to add atomic properties on our group communication. Okay? What is atomicity? It's all, all or nothing, right? So think of a case where sender does a multicast. Okay? And the multicast library actually has to internally send out n messages. Okay? Sender does one send, the multicast library makes it n sends and it's sending them out. And let's say the machine crashes in the middle. Some subset of the receivers have received the message, the others never received the message. Okay? So now you have your group, not everyone got the message. Okay? Sender crashed while sending it. Okay? Now this can cause higher level application a problem, because let's say this was a banking example where you had sent, your send was a query saying add $100 to this person's account because they deposited $100 check at the ATM. Okay? So you are sending a multicast messages to n of your banking databases. Okay? You send to the first 3 and the sender crashed. Okay? So the first 3 updated it, the others did not. Okay? Now your system has gone out of sync. Okay? So if you have group communication where send only reaches some subset and there is some failure in the system, it can cause higher level problems. So you might want atomic properties where the multicast library says either I deliver the message to all the recipients or I don't deliver it at all. Okay? If it goes to a subset, then you undo it and say throw it out, okay, because it's not successful delivery, and then everyone throws it out. So you basically, it's like it was never sent. Okay? So this is going to add this higher level property called atomic multicast. This is a higher level guarantee you will give. Okay? This requires much more mechanisms than simple retransmits and whatnot. Okay? But the way it's implemented in distributed system libraries is through this notion of a group view. Okay? A group view basically says that each process has a view of what other processes are alive in the system. Okay? And the assumption is while the processes are alive and are working, the group communication will actually occur successfully. When you send, they'll all receive it because everything looks okay. All the processes are up. The network is fine. We assume your TCP is being reliable and all this kind of thing. Okay? The problem is going to occur if some process in that group is going to crash. Okay? If it crashes, that means that maybe you are in the process of sending some message. That process did not receive it. Your receiver crashed, not a sender. Okay? Sender can also crash. Okay? So the way one building block to build atomic multicast is to track when process failures occur and the group itself changes. Okay? So this is essentially what is being shown here. Okay, so the group initially has 4 processes, P1, P2, P3, P4. At some point, okay, and so you'll see the first 2 sets of messages, they reach everyone else in the group. Then P3 has crashed. Okay? At this point, any message in transit will fail. If you want atomic properties, it will fail and you will undo it. Okay? But now you want the system to not stop working saying 3 has crashed, so no more messages can be sent. That doesn't work. So what you will do is you will identify a new group saying P3 is gone. Okay? We will now say that the remaining processes are P1, P2, P4. The application will acknowledge that you have now a smaller group, and any subsequent send will only be guaranteed for P1, P2, and P4, because fundamentally at this point P3 is crashed, so you cannot deliver message to P3 until it comes back. Okay, so long as at a higher level the application can deal with a fault of P3, you will accept this group change saying, okay, next set of messages will only go to the smaller group, and you will continue to send it. And at some later point, you will see that P3 has restarted. Okay, you will restore the original group, and there has to be some higher level recovery because P3 has missed some messages. If this was a database, you have to catch up and so on. That's not shown here. Okay, this is simply telling you how sends and receives work. Okay, so you will keep track of what's the current group, make sure that all or nothing property applies to that group. Whenever there's a failure, you have what's called a group change, and then you tell the application group has changed, and all subsequent guarantees are for that new group, which is smaller, and then you continue to have atomic delivery of messages to this group. Again, maybe P3 rejoins, the group changes again, and so on. So you have to keep track of these group changes to ensure atomic multicast is always in play. Okay, because whenever there's a failure, at that point, if you don't change the group, you cannot deliver any more messages, okay, because your atomic properties will prevent you from doing it. Is that clear what I said? Yes to your question. Okay, the question is, so in this example, when P3 disappeared and rejoined at a later time, P3 has missed some messages, what will happen? Okay, so clearly P3's state has to be synced with P1, P2, and P4, okay, for the system as a whole to continue to run. That's not going to be handled by the network library. Okay, it's not like the multicast library has stored all the messages that P3 has missed and delivered it, because the atomic guarantees had changed. They were only being delivered to P1, P2, P4. That has to be handled at the application level. Okay, so again, if this was a database application where P1, P2, P3, P4 are running databases, when P3 joins, okay, you can use something like logs, right? So you will basically, P3 will say, send me all the transactions that I missed. So you will send the transaction logs. It will say these were the ones it missed. It will replay those logs. It will catch up. Okay, and then when its state is synced with P1, P2, and P4, it will rejoin the network. So those things are handled at an application level. They are not going to be handled by the multicast library. This thing is only guaranteeing all or nothing property for a set of processes. Okay? And whenever the process crashes, it will change the group view. That's all it will do. Okay? But yes, that's an important thing to deal with. Right? You can't just ignore that P3 is out of sync and it rejoins and just starts as if nothing had happened. You have to deal with that. Okay, but we'll get to the database and all of those parts in a little while. All right, so there was a system designed at Cornell, name was ISIS, that came up with this idea. The name is unfortunate in the current context, but that's 25, 30 years ago. Okay, so they came up with this idea of atomic multicast. I will not get into the details of what it did, but basically it used this notion of a view change, that what this example showed, it could actually keep track of which processes are up, which processes fail, keep changing the group, tell the application, but for whatever group the application agreed to, it would guarantee an all or nothing property. Okay, that's what it did. We don't need to go into the details of it. I just wanted to mention that this idea was designed maybe 25, 30 years ago at the system that was built at Cornell. They actually spun it out as a company as well at some point. And then they sold it to banking, financial companies, and so on, this product. Okay, so that's all I will say about atomic multicast. I'll summarize this and we'll talk about distributed commit. So what this slide is showing you are that there is many ways to implement group communication. Okay, the simplest approach we saw was a NAC-based scheme that scaled. That was just doing reliable multicast. Okay, it just made sure that when a message is sent, all the recipients receive it. Okay, so there was no message reordering guarantee. There's no guarantee across sends of messages across machines or anything like that. Okay? Then we said you can add FIFO guarantees on top of reliable multicast. That gives you FIFO. What that simply does is for each sender, you send messages and receive them in the same order. Across senders, you might get messages in different order. You might get one from one, two from the other, and then some other receiver might get two first and then one. Okay, but each sender's messages come in order. Okay? Causal and essentially added causal delivery, where if two sends were ordered across processes, it guaranteed that the received at all the group within the group were also ordered. Okay? And so that added causal delivery. Then we said atomic properties, where you are going to not get any message ordering, but you will essentially get atomic properties, all or nothing. And then you can combine them. You can have FIFO atomic, you can have causal atomic, all kinds of combinations. Okay? So what this is simply telling you is that it's not enough to just add reliability, which is what TCP/IP does. For higher level properties in distributed systems, you may need stronger properties. That's really the takeaway here. Is that clear? Yes, your question.
Order delivery should imply basic message order, right?
Yes. So total order delivery should typically imply basic message ordering. So the question is, what does basic message ordering mean? So here it simply means FIFO ordering. So yes, total ordering will mean FIFO ordering. So that none there is not correct. It will at least give you that. Yes, I would agree. This is taken from the book, but yes, you're right. Yes. The question is, if you use a NAC-based scheme, if you have the last message in the sequence, how does a receiver that doesn't receive it figure out it has to send a NAC? The question clear? Okay. So the answer is you have to send an additional dummy message saying I'm done, or something like that, right? Because otherwise you will not know. That's why you might have to send one or more of these and make sure that you get a NAC. Yes. Does total order guarantee FIFO ordering? So if you look here, right? So what does total order says? If a process receives M1 before M2, all processes receive M1 before M2. Right? So you have imposed some total ordering. Okay? Now, typically total ordering actually uses FIFO ordering and then also orders across processes. Okay? But total ordering does not actually have to respect FIFO ordering. You could just declare that this is the order, okay? And you might have violated FIFO order. So long as all processes agree on that order, that's still a total order. Okay? But a more practical total ordering will always ensure FIFO ordering, because why would you deliver process messages out of order? That causes problem for the application. So I send request 1 and I send request 2. If you get them in out of order, that might cause some problem. So practical versions of total ordering, yes, they should guarantee that. But total ordering by itself doesn't say I have to respect FIFO ordering. It just says I should make sure all processes see messages in the exact same order. Okay? Whatever order is decided, it doesn't have to respect FIFO. But in practical cases, it should imply. Okay? Yes. Okay. So we will now talk about distributed commit in the next 5 minutes. We'll continue that next time. So the problem of atomic multicast, you can think of it as a special case of a more general problem. Okay? So what is atomic multicast? Atomic multicast says all processes that are receivers either get a message or nobody gets the message. So the operation here is the sending and the receipt of a message, and you are imposing an all or nothing property on that operation. Okay? But you can now make this operation any arbitrary operation and say, I want all or nothing property on top of it. Right? So we already talked about transactions. So it gave all or nothing property on a set of instructions. Right? So we will now generalize that to this problem of distributed commit, where we don't care what the operation is. A group of processes want to perform an operation, any abstract operation. It's a processing of a request. It could be receipt of a message. It could be anything else, writing to a file. You think of any operation that a process wants, and you want all or nothing property on a group. That either all of them perform that operation successfully or none of them perform it. Right? If the operation is receipt of a delivery of a message, then this distributed commit will implement reliable multicast. If this operation is committing of a transaction, you are implementing a distributed database commit. Right? But we don't really care. We are just going to give this general library that says you pick the operation, okay? And this library will now guarantee that either all of them perform it or none of them perform it. Okay? So that problem is called the problem of distributed commit. Okay, so we will have this all or nothing property. So now you have this nice abstraction that you can use for all kinds of things in a distributed application. If you had a library that gave you distributed commit property. Okay, so question is, how are we going to do this? Okay, I'll show you a very simple example today, and then we'll talk about it next time. So we will see a technique called two-phase commit, which is called 2PC, very old technique. It was designed in 1978 that gives us this all or nothing property. It was designed for databases, but you can generalize it for any arbitrary operation. And then we will also see a generalization of that to say three-phase commit. Okay, but I'll just show you what it does, and then I'll discuss it next time. Okay, so this two-phase commit essentially needs a coordinator. Okay, and this coordinator is going to decide whether all the processes should successfully perform the operation or they should discard the operation because it's all or nothing. Okay, so how are we going to do this? The idea is very simple. We are going to use voting. Okay, the coordinator. So one of the n processes becomes the leader. You have a leader election. You say one of the processes is the leader. It becomes the coordinator to implement distributed commit. What this coordinator is simply going to do is it's going to ask all the processes, did you perform the operation? Okay, or should we commit the operation? Let's just ask that. So every process is going to vote yes or no. Okay, so either the operation should finish successfully or not. So you get to vote yes or no. Okay, if everyone votes yes, the coordinator will tell all the processes, go ahead and commit. Everybody has successfully finished this. Now let's commit it, which means all of the processes are finished the operation. Okay, if anyone votes no, the coordinator will tell all the processes, throw away that operation because it did not finish at least one, so it should be nothing. Okay, so undo everything. Okay, very simple voting approach. You ask everyone, should we commit? Everyone says yes. Answer is commit. If anyone says vote, it's like a veto. It's not a majority. No means veto. Right? It's not like 10 of them said yes, one said no, so we'll say yes, we'll take majority. No, because it's all or nothing. Even if one says no, everybody has to do no. Right? So you'll say throw it out. So we will abort the transaction. Okay, so we'll come back to this. This is just showing you a state transition diagram of how to do this. So it's basically going to be a simple voting protocol, and it's two-phase commit because there are two phases. In first phase, you ask, you get votes. In the second phase, you tell everyone what to do, commit or abort. Right? So that's why there are two phases, but we'll talk about this next time. All right, so we'll stop here today.